parts inside the engine would fail, and both of these drawbacks were largely due to the steel turbine blades. Something that occurred to me is, why aren't they made out of tungsten? I mean, because tungsten doesn't melt until 3,400 degrees Celsius, which is more than twice the temperature inside a modern jet engine. But tungsten is also incredibly dense. It's about 2.5 times denser than steel, and it's also brittle, which makes it hard to manufacture. And using a material that heavy wouldn't just make the blade a problem, the components that hold the blade in the engine would also have to carry much higher loads, well beyond what current materials can handle. So you can optimize for one thing, like the melting point, or a different thing, like strength or weight, but the turbine pushes every variable to its limit. So what are these blades actually made of? Well, to find out, we went to Rolls-Royce's precision casting facility in Derby. And it turns out the world's most advanced metal parts begin life as, well, something surprising. What is with the pink and the green there? I'll come and show you. I'm just seeing so many cool things around here. I was like, what is that? Why does it look like that? You just enter this room, and I smell the wax. Yeah. It smells like a candle factory in here. Absolutely. So investment casting is a really, really ancient technology. So our ancestors have been doing investment casting to make jewellery, to make weapons for millennia. We've just perfected it here to make turbine blades. It's so wacky. This is just not how I'd expect it to happen at all. Turbine blades strike me as one of the most high-tech things in the world. Yep. And yet, this facility is using wax as a starting point. What you will see through our tour today is that actually it's a really highly technological process. This is our wax pattern die. This is how a turbine blade starts its life. So this is what's going to go inside the wax pattern. A ceramic core. This is going to create the hollow inside the turbine blade. So what's happening now is we're injecting into the die. So that's the very start of the life of a turbine blade. That is really neat. What we'll actually see is that a lot of these features, such as the aerofoil and the annular surfaces, are not touched further. So we will cast that, and that will remain as cast as it goes into the engine. Every surface here has to be perfect, because this wax is what will become the blade. So Kim is our wax pattern assembler. So she's responsible for taking the product straight from that die, making sure that things like die lines have been removed, so where the die blocks come together and leave a small amount of flash. The operative word in all of wax assembly is smooth. Every tiny imperfection in the wax would become a flaw in the metal, so this takes an incredible amount of skill. Then it's the case of getting that wax pattern attached to the unit runner to create the assembly. I mean, the thought that occurs to me, right? Shouldn't you be doing this with a robot? Yeah. So Rolls-Royce has facilities that do this by robot, but our facility in particular is very much focused on bringing in those new products, and it's far, far easier for us to work with human beings to develop that method of manufacture that's going to bring the next generation of product through. I'll bet. I can see the skill here. Absolutely. It's phenomenal. I'll just make a mess of it. Absolutely, yeah. So would I. No. Once the wax assembly is perfect, it's ready for the next stage. Everything that is wax is going to become air. It's going to become negative space, right? It's going to become our cavity. And then we're going to fill that air with metal.
If it's your turn.
So we take that wax assembly and we've got to build a shell. The shell is made of many different layers. It's a zircon-based shell system. We're going to dip into a primary slurry. It's really quite thin, like a light syrup or a thin honey. Oh, yeah. And what that's designed to do is map all of those really complex geometric features. Beautiful. It's like making icing. So that's actually the analogy we use. So it's a bit like if you put icing on top of a bun or a cake, you need to sprinkle it with some sugar afterwards, otherwise it's all going to slop off the top. So we've got the slurry on there, we're going to get a nice even coat, drain it, make sure that it's an even thin layer, and then we're going to sand, and that's then going to set that layer in place. So cool. Whoa. We're then going to dry it, so it's air dried for many, many hours, and then we can create our backup layers. So our backup layers is a much thicker slurry, more like a treacle, and the sand is much coarser, more like a granulated sugar. And we're going to maybe put 4, 5, maybe even 6 layers to back up, because what we need is a mould that can withstand the casting parameters that we're putting it under. You know, it's got a lot of work to do. The wax is then melted out, and the mould is fired. Oh, yeah. As well. Cleaned and tested to make sure there aren't any cracks. When it's done, the shell is ready to hold molten metal.
This is a billet of alloy that's going to fill the whole of that mold. So just that amount of metal is going to fill that whole mold there.
It doesn't look like enough. This is a nickel alloy. The first nickel alloys used in jet engines were developed in the 1940s. By adding chromium and cobalt, engineers created alloys that could handle 800 to 900 degrees Celsius, around 100 degrees hotter than the steel used before. And these alloys could keep their strength for thousands of hours, a tenfold improvement in life. But the real breakthrough came when they added a touch of aluminum. So we wanted to see how it held up under the same lab conditions as the steel and titanium.
What temperature are we at now?
No, that's 700 degrees.
700. So steel's long gone.
Steel's long gone. That's 800 degrees. 800, yes.
In fact, around this temperature, it's actually getting stronger. So why would heating a metal make it stronger? Well, when these nickel alloys were first used in jet engines, no one actually knew. But about 10 years later, electron microscopes had improved enough for engineers to finally see what was happening inside. As we zoom in on the alloy, a pattern emerges. The microstructure isn't uniform. Instead, it kind of looks like a city grid, made up of blocks with roads in between them. Only each block is so small, over 300 would line up across the width of a human hair. Now, surprisingly, both the roads and the blocks are made up of the exact same atoms, mostly nickel with a little aluminum. They even have the same crystal structure, a grid of tiny cubes with atoms sitting at the corners and at the center of each face. The only difference is that the atoms are arranged slightly differently. In the road structure, the aluminum and nickel can take any spot. There is no repeating sequence from cube to cube, and this is known as the gamma phase. But in the blocks, aluminum always takes the corner spots and nickel the faces, and you get a perfect repeating pattern cube after cube. This is the gamma prime phase. And it's this difference that is crucial when a dislocation tries to glide through the lattice. In the roads, this motion is easy. Each layer of atoms can shear smoothly past the next, leaving the structure looking unchanged behind it. But if you try to do the same thing in the blocks, well, now you're actually changing the order of the atoms. Nickel and aluminum end up sitting in the wrong places. That takes energy, so the lattice resists it. So when a dislocation moving through the roads hits a block, it gets stuck. And that's what makes this alloy so strong.
But if you keep pushing and the stress gets high enough, dislocation can finally force its way in. The catch is that this dislocation leaves the lattice in such a high energy mess that the only way that it can keep moving is if there's a second one right behind it that puts things back in order. So in the gamma prime phase, dislocations have to travel in pairs, called super dislocations.
I need that creation of those super dislocations, and I need that very high stress to be able to shear. So that's why the strength is very high relative to other alloys. What happens is ultimately, because you're shearing through that gamma prime with two dislocations, as the temperature continuously increases, you're adding more and more thermal energy in the material. What happens is the atoms are going to vibrate more and more and more. So there's a likelihood, as I'm doing this and I'm oscillating in 3 dimensions, that the thermal energy is going to drive me to actually slip down, rather than just slip in one plane. So now if one cross slips, they're no longer on the same plane. Think of it as if we're standing in line, and the only way that you can move is if I push you, right? And then I keep on pushing you, and then suddenly you drop. So if I now try to push you, I cannot find you, right? You're not in front of me anymore. Your shoulders are now below me. Why are you touching me? I should have used the other example, you pushing me, but anyway. But it's exactly that. It's the exact same analogy. There's nothing to push me anymore. I am not able to do it.
So now you've got these two dislocations that are on different planes, so they can't travel together anymore. And as a result, they're both now locked into place. And you can see that effect on this graph. While steel and titanium strength drops off, in the nickel superalloy you actually get a peak. That's because the extra thermal energy lets more dislocations cross-slip and get separated. And it's that shuts down the motion of dislocations.
Some magic, Sarah. Going magical.